All right, let's talk about some more Eriksson problems. So this is chapter 6. We're doing Galerkin methods, and we want to compute the L2 projection into P3 of our exact solution U and compare it to capital U. And so in this problem statement, I don't really like this because it's not very clear what they're asking you. Because what they're actually asking for is they're actually asking for specific values u0, because the at the beginning of this chapter we have in general ut. Well, this method works for any like L2 function u. I think L2 is what you need, but there's a particular problem at the beginning of that we're using as an example, whose exact solution is given by u0 e to the lambda t. Because the problem is a function whose derivative is equal to itself times some constant lambda, and which satisfies, and which is equal to a constant u0 at the point x equals 0. And so, of course, this is a solution to that. And so this question you're not really able to move forward at all unless you have like something that you can work with. So you need to like choose a specific function u that you can work with. So you have to first make the step down in generalization to go from, okay, we're not looking at general functions u, we're actually looking at this specific solution, u naught e to the lambda t. But furthermore, you actually have to go through and be like, okay, well, this is still like there's a lot of constants here, so we need to step down another level in generalization, choose values for u naught and lambda. So it's a little unclear from the problem statement what level of abstraction they're asking for, but it turns out that they want you to really like look at something that you can really get your hands on. And they even did this a little earlier in the section, where they set u0 equals lambda equals 1, and with that they actually provided a what the actual Galerkin approximation capital U looks like in like a decimal form, and we'll derive that all here. But anyways, so just to be clear, this is the problem. We want to find the L2 projection of this solution. So if you make so if u0 is 1 and lambda is 1, then it's just ut equals e to the t. So we want to, no, not u to the t, e to the t. So we want to take this function and project it into P3 and compare it to our Galerkin approximation. So just as a reminder of what was discussed in the text, the Galerkin approximation was given by u is 1 plus sum from blah blah blah. The top here, this 3, this is because we're projecting into P3. And then xi1, xi2, xi3. There is a thing. There it is. Yeah. So this formula over here, 6.4, this formula tells us what these xi should satisfy. It gives us a system of equations in terms of xi's, and of course we've got this lambda and this u0, but we actually solve for specific values here. And so like down here they actually derive this Galerkin approximation capital U, but we'll actually derive it as well because, I don't know, why not? Might as well. Oh, that's right. I mean, I'm like, what's going on? Okay. So, well, I should probably say no. Whatever. Okay, so returning to this. Oh man, I'm going to be late for an appointment. So, we are going to actually derive this formula. And so how we're going to do that is going back to that system. If you actually write out what it is using these specific values of I and j or whatever, it turns out to be this really lovely looking matrix. And so at this point, like, yeah, I mean, this part of the problem, you probably don't need to do this, but I felt like I would, just to like actually see how you get this Galerkin approximation capital U. Anyways, I saw this. I'm like, I'm not gonna solve this. So I just made a MATLAB code that makes it. So you make this A, and this formula here, if you look in the textbook, that's the formula that's used for these indices here. And then you make that matrix here. So this is A, x equals b. So you make A, then you make b, and then you just solve for x. You don't use any fancy methods. You just use the built-in MATLAB thing. And then, of course, I made an extra thing here that makes it easy for me to transfer it into LaTeX so that we get this. And we'll actually write out these numbers later on, and you'll see that it's approximately the decimals that they provide in the textbook. Although I think I use more decimal places because I just took whatever decimals MATLAB threw at me, I just copied and pasted them. But anyways, so that's how we find U. So I guess I haven't technically found U. I've just found these coefficients, but whatever. All right, so now let's actually get into the real work in this problem, which is to actually compute the L2 projection. And we'll compute this projection by pi mu. So of course this is not the scalar pi times the function u. This is just pi is being used as the Greek letter for p, so it's projection. P for projection, yeah. So we want this to be a function in P3, and we want to ensure that it satisfies this integral equality for every single v in P3. So this is actually sort of a tall order. Like, it's not obvious just from looking at this that you're able to find anything that does this. But you actually write out, like, you try to break this down a little bit. And so let's see here. We know that v has a basis given by tk. I guess I should probably say that, since let's see here. So we have t to the I from I equals 0 to 3 is a basis for P301. It suffices to guarantee that this integral is 0 for k for all of these basis elements here. So this t to the power of k, those are the basis elements. All right, and we know pi u, this projection is, well, we're projecting into P3, which means that it's a cubic polynomial, which we can write as this for some constants a, b, c, and d. And so basically we obtain four integral equations in the unknowns a, b, c, and d. If you plug in k equals 0 through 3 here, and you just plug in a, b, c, and you plug in the formula for pi here. And again, now the previous one, like, I could have done it by hand, but it was a lot easier to use MATLAB. Here, you don't want to touch this without MATLAb, because basically, this I0, basically, what you have to do is you have to integrate from 0 to, you're integrating from 0 to 1, e to the t minus at cubed minus bt squared minus ct minus d, which is just this thing. And of course here you're just multiplying by v equals 1 so that you don't even include that. And it's an indefinite integral, you can do that. You get to I1, you have this constant t here, so you got to use integration by parts in order, and let u be t and v be this entire thing. And then you use that to solve it. And I didn't continue from there because what I think happens is, my guess is that for I2, you have to use integration by parts once for u equals t squared and dv equals this thing. And then they'll give you like something involving these things which is evaluated from 0 to 1. And then the other term in the integration by parts formula will be t times the antiderivative of this term. And in order to solve that, I think you need to do integration by parts again, just like you did in I1. So basically for ij, I think you need to do integration by parts j times. And that's way too many integration by parts for me to do by hand, so I just told MATLAB, hey, look at these things. I just told MATLAB, okay, so just algebraically using these symbols, set these equal to 0 and solve it. And it works. It gives you an output. It's really, really big numbers involving e's, but hey, it works. I would not want to do this by hand. I don't have time for that. That's not what I signed up for when I, well, if I had to do it, I would, but I don't have to, so why would I? Okay, so what do we have now? We have U, capital U is given by this, and pi u is given by this. Again, this is this 30 over 29, that's I1, this is I2, this is I3. So yeah, and then, okay, so how close are these? There's no way to tell by looking at it this way, but you tell MATLAB to give you decimals, and it looks pretty close. And you look at the difference, and these are all, it's like 0.0 something for each of these. So the difference between mu and pi u is relatively small. Relatively is, of course, like, that means nothing mathematically. This really doesn't, it's sort of tough to, like, if you were doing this rigorously, like, this doesn't really tell you much. If you really wanted to make sure that this method was working, what you would have to do is you would have to, like, compare this for different values. So this was for we were in P3 here, so we had Q equals 3. You would have to compare it for different Q values and then look at the norm of this difference, like with respect to some norm that you've placed on this polynomial vector space, and then see the rate at which this, or see what happens to the error. And as Q increases, the error should increase, the norm of this difference should increase. And there's probably, like, I think there should be some way to, like, some analysis you can do to just get, like, an upper bound on the difference, and I'm sure there's, like, some order of accuracy to the error. I don't know for sure. I haven't gone that much further in this textbook, but there's probably an order of accuracy for this procedure, and then you would compare that order. You would look at the ratios of the norms of these differences and see if the ratio gives you a number that corresponds with what the order of accuracy would be. So basically, by itself, this doesn't tell you that you've got a good approximation, but it looks pretty good just from a naive perspective. And so, yeah, that's about all we need to do in this problem, and so we're done.